In Korea, winter imposed constraints that planning alone could not overcome. The peninsula's climate featured continental weather patterns that brought extreme cold from Siberia during winter months. Temperatures in the northern regions regularly dropped to 20 or 30 degrees below zero Fahrenheit. Wind increased the effective cold beyond what thermometers measured. Snow covered the landscape for months, transforming roads into treacherous routes and concealing terrain features that affected movement. These conditions were not unknown to military planners, but the severity and duration exceeded what most American forces had experienced or trained for. Winter became an operational factor that shaped decisions at every level, from individual soldiers managing personal equipment to commanders planning major operations. American forces entering Korea during the summer and autumn of 1950 faced initial combat operations in moderate temperatures. The focus was on tactical situations, enemy dispositions, and terrain control. As autumn progressed into winter, temperature became an additional consideration that gradually moved from background concern to primary constraint. The transition occurred over weeks rather than suddenly, giving units some time to prepare but not enough to fully adapt to conditions unlike anything most soldiers had previously encountered. Initial preparations for winter operations included requisitioning cold weather gear through supply channels. The equipment available included parkas, insulated boots, gloves, and sleeping bags rated for cold temperatures. However, supply quantities did not match the numbers of troops requiring equipment. Distribution prioritized units in forward positions, but even those units received incomplete issues. Some soldiers received full cold weather outfits, while others made do with standard uniforms supplemented by whatever additional layers they could obtain. The inconsistency in equipment availability created disparities in cold weather protection that affected casualty rates and operational effectiveness. The cold weather gear that did arrive had been designed for temperatures common in northern United States or Europe, generally above zero Fahrenheit. Korean winter temperatures frequently dropped well below zero, exceeding the protective capacity of the issued equipment. Soldiers wearing full cold weather gear remained vulnerable to frostbite during extended exposure. The gear also had practical limitations. Thick gloves made it difficult to operate weapons or perform detailed tasks. Heavy parkas restricted movement and created bulk that complicated getting in and out of vehicles or fighting positions. Insulated boots, while warmer than standard boots, were larger and made walking on steep or icy terrain more difficult. Daily routines changed substantially as winter deepened. Morning began with the challenge of becoming mobile after a night of cold. Soldiers who had been sleeping or resting in whatever shelter existed faced the physical difficulty of movement after hours of near immobility in extreme cold. Joints stiffened, muscles ached, and the simple act of standing required effort. Equipment that had been set aside overnight often froze, requiring time to thaw or force into operation. Weapons needed checking to ensure actions had not frozen. Vehicle engines required extensive preparation before starting. The process of preparing for a day's operations in extreme cold consumed hours that would have been available for movement or tactical activities in moderate weather. Soldiers emerging from sleeping bags faced immediate exposure to temperatures that could cause frostbite within minutes on exposed skin. The first task involved putting on layers of clothing in a sequence that balanced warmth against the need to remain mobile. Too many layers restricted movement and caused sweating, which would freeze later. Too few layers provided inadequate protection. Experience taught the right balance, but new soldiers often made mistakes that led to cold injuries. Breakfast in extreme cold presented challenges beyond simple food preparation. Rations that had frozen overnight required thawing. Field stoves designed for moderate temperatures functioned poorly or not at all in extreme cold. Fuel for stoves became thick and difficult to ignite. The time required to prepare hot food increased substantially, and in some cases, units simply distributed cold rations that soldiers attempted to thaw using body heat or small fires when operational security permitted. The nutritional value of frozen rations consumed cold was questionable, but hunger drove consumption regardless of temperature or palatability. Movement during winter operations occurred more slowly than during moderate weather. Soldiers carrying equipment through snow expended significantly more energy than walking on clear ground. The weight of cold weather gear added to the burden. A soldier might carry 70 or 80 pounds of equipment, including weapon, ammunition, rations, water, sleeping bag, and personal items. Adding bulky cold weather clothing increased the total weight and changed the distribution of that weight across the body. Movement through knee-deep snow with this load exhausted soldiers quickly. Frequent rest stops became necessary not just for physical recovery, but to check for signs of frostbite or exhaustion. Squad leaders learned to watch for symptoms of hypothermia in their men, including confusion, slurred speech, and loss of coordination. These symptoms indicated dangerous drops in core body temperature that could prove fatal if not addressed. Treatment required warming the affected individual, which meant stopping movement and using precious fuel or body heat from other soldiers. Each stop for medical reasons further slowed overall movement and consumed time that tactical plans had not allocated. Units that might cover 20 kilometers in a day during summer found themselves struggling to cover half that distance in winter conditions. This reduced mobility affected operational planning and limited commanders' options for maneuver. Movements that appeared reasonable on maps became impossible when attempted in actual conditions. The gap between planned movement rates and achieved rates created cascading problems in operations that depended on units reaching objectives by specific times or coordinating movements with other units. Guard duty and observation posts presented particular challenges during winter nights. Soldiers assigned to these duties faced extended exposure to cold with limited ability to move around to generate warmth. A 2-hour guard shift in 20 below zero temperatures created genuine risk of frostbite or exposure injuries. The soldier on guard needed to remain alert and observe assigned sectors, but the cold made sustained attention difficult. Stamping feet and swinging arms to maintain circulation created noise that could compromise security. Remaining still allowed cold to penetrate more deeply. Units experimented with shorter shifts to reduce exposure time, but this increased the rotation frequency and reduced rest time for all personnel. A platoon with 40 men maintaining 4 guard posts around a perimeter needed to rotate guards frequently enough to prevent cold injuries. With 1-hour shifts, each soldier might stand guard 3 or 4 times during a 12-hour night, severely fragmenting sleep and rest. Some units established warming stations near guard posts where soldiers could briefly warm themselves, though this required fuel and created light discipline concerns. The balance between maintaining effective observation and preventing cold casualties became a constant command decision. Weapons performance degraded significantly in extreme cold. The M1 Garand rifle, standard issue for most infantry, generally functioned in cold weather but required careful maintenance. Oil used for lubrication in moderate temperatures became thick and sluggish in extreme cold, increasing friction and slowing the action. Too much oil could cause the weapon to freeze entirely. Soldiers learned to use minimal lubrication or to strip weapons nearly dry, accepting increased wear in exchange for reliability. This created long-term maintenance problems as weapons wore faster, but immediate functionality took priority. Ammunition also presented problems. Rounds kept in cold conditions sometimes failed to fire or produced reduced chamber pressure. The primers and cartridges could freeze, preventing ignition. Powder charges were affected by extreme cold in ways that reduced burning rates and chamber pressures. The result was that some rounds failed to fire at all, while others fired with reduced velocity and effectiveness. Soldiers learned to keep loaded magazines inside their clothing to maintain ammunition at body temperature. This meant carrying fewer loaded magazines immediately accessible, since only 1 or 2 could be kept warm against the body at any time. Machine guns faced more severe cold weather challenges. The Browning automatic rifle and .30 caliber machine guns required lubrication to function properly, but finding the right balance between preventing friction and preventing freezing proved difficult. Crews cleaned and checked weapons multiple times daily, sometimes hourly, during extreme cold. The process of field stripping a machine gun in 20 below zero temperatures while wearing gloves was nearly impossible. Removing gloves to perform detailed disassembly exposed hands to immediate frostbite risk. Crews learned to work in shifts with one man performing tasks barehanded while another warmed his hands, then switching. Belt-fed ammunition was particularly vulnerable to freezing. Metal links and canvas belts became stiff and prone to jamming. The belts needed to remain flexible to feed smoothly through the weapon's mechanism. Cold made the canvas brittle and the metal links rigid. Crews tried various solutions, including keeping ammunition belts inside sleeping bags or wrapped in blankets. Some applied light oil to links, though this could create its own problems if the oil froze. The constant attention required to keep ammunition functional consumed time and attention that should have been available for other tasks. Water-cooled machine guns risked freezing coolant, which could crack the jacket and disable the weapon. The .30 caliber machine gun used a water jacket around the barrel to prevent overheating during sustained fire. In extreme cold, this water could freeze and expand, cracking the jacket. Crews had to drain coolant during extreme cold or add antifreeze when available. Antifreeze supplies were limited, and not all crews received adequate quantities. Some crews learned to use other liquids, including vehicle engine coolant drained from trucks, though this was not recommended procedure. The improvisation kept weapons functional but created non-standard conditions that could cause other problems. Vehicles experienced numerous cold-related failures. Engine oil thickened in cold temperatures, making engines difficult or impossible to start. The viscosity of oil changed dramatically as temperature dropped. Oil that flowed easily at 60 degrees became nearly solid at 20 below zero. Starter motors could not turn engines through this thick oil. Batteries lost power rapidly in extreme cold, reducing starting capability. A battery at full charge in moderate temperatures might retain only 30 or 40% capacity at 20 below zero. The combination of thick oil and weak batteries meant that cold engines often would not start without extensive preparation. Fuel could gel or freeze, blocking fuel lines and filters. Diesel fuel was particularly prone to this problem. The paraffin in diesel fuel began solidifying at temperatures common during Korean winters. Once fuel lines froze, vehicles became immobile until the fuel thawed or lines were replaced. Gasoline vehicles faced fewer fuel problems but were not immune. Water contamination in fuel systems could freeze and block fuel flow. Fuel filters became clogged with ice crystals that formed as temperatures dropped. Cooling systems required antifreeze, but supplies were limited and not all vehicles received adequate protection. Radiators and engine blocks could crack if coolant froze. The damage from frozen coolant was often catastrophic, requiring engine replacement rather than simple repair. Maintenance personnel learned to drain cooling systems at night and refill them in the morning, but this consumed time and antifreeze. Some units mixed whatever antifreeze they could obtain with water in ratios that provided partial protection, accepting the risk of freezing at extreme temperatures rather than accepting certain freezing with pure water. Tires became stiff and lost elasticity, increasing susceptibility to damage on rough roads. Rubber compounds hardened in extreme cold, making tires brittle. A tire that might flex over a rock in moderate temperatures could crack or tear in extreme cold. Flat tires increased dramatically during winter months. Changing tires in extreme cold was miserable work that exposed soldiers to frostbite risk while struggling with frozen lug nuts and brittle valve stems. Tracks on armored vehicles became brittle and more prone to breaking. Track pins that held links together could snap under stress that they would normally withstand. The cumulative effect was that vehicle availability decreased significantly during extreme cold periods, limiting mobility and logistics capability. A company with 40 vehicles might find that only 20 were operational on a given winter morning. The others awaited repairs, thawing, or simply would not start, despite all efforts. This reduction in mobility affected every aspect of operations, from tactical movement to logistics resupply to casualty evacuation. Commanders learned to plan, assuming that half their vehicles might be unavailable at any given time during extreme cold. Starting procedures for vehicles in extreme cold became elaborate rituals that consumed hours each morning. Crews learned to drain engine oil at night and warm it over fires before refilling in the morning. This required fires, containers to hold oil, and time for the oil to warm sufficiently. Engines were started periodically through the night to prevent complete cooling, though this consumed fuel and required personnel to remain awake. A truck might need starting every 2 hours through a 12-hour night, using fuel simply to keep the engine from freezing solid. Battery blankets and engine covers helped retain heat, but were not always available. These items were low priority in supply distribution compared to ammunition and food. So many units operated without them. Improvised engine covers made from canvas or blankets helped, but were less effective than purpose-designed equipment. Some units built fires under vehicles to warm engines before starting, accepting the fire risk as preferable to immobile vehicles. This practice was dangerous, occasionally resulting in vehicle fires, but desperation drove acceptance of risks that would have been unthinkable in peacetime. These procedures consumed hours each morning, delaying operations and absorbing manpower that could have been used for other tasks. A platoon might need to dedicate 4 or 5 men for 2 or 3 hours simply to get vehicles started. These men were unavailable for guard duty, maintenance of other equipment, or preparation for movement. The time consumed by cold weather vehicle starting procedures forced earlier wake-up times and later departures than tactical plans assumed. Communications equipment functioned erratically in extreme cold. Radio batteries lost power quickly, their chemical reactions slowing as temperature dropped. A battery that provided 8 hours of operation at moderate temperatures might last only 2 hours at 20 below zero. Radio operators learned to keep spare batteries inside clothing to maintain warmth. Even with warm batteries, radio performance degraded in extreme cold as components contracted and connections loosened. Solder joints could crack. Vacuum tubes, still common in radios of that era, became more fragile. Range decreased as component performance degraded. A radio that normally transmitted 10 kilometers might manage only 5 in extreme cold. Transmission quality deteriorated with increased static and signal distortion. Receiving weak signals became more difficult. The combination of reduced range and degraded quality made communication unreliable precisely when it was most needed for coordinating operations in difficult conditions. Radio operators became specialists in coaxing performance from equipment operating outside. Design parameters. Wire communication proved more reliable than radio in some respects, but laying wire through frozen ground and maintaining it during snow and ice required constant effort. Wire teams used picks and axes to create shallow trenches through frozen ground. The wire itself became brittle in extreme cold and could snap when handled roughly. Snow and ice accumulation on wire created weight that pulled down lines or broke connections at terminal points. Maintaining wire communication required continuous patrol of lines to identify and repair breaks. Units experienced communication failures at critical moments, forcing reliance on runners and creating delays in coordination. Runners carrying messages between units faced the same mobility challenges as other movement, compounded by the need to travel alone or in very small groups. The time required for a runner to carry a message and return with a reply could measure in hours when distances and terrain were significant. This communication delay affected tactical decision-making by creating gaps between when situations developed and when commands could respond. Frostbite emerged as a major source of casualties independent of combat. Exposed skin could freeze in minutes at 20 or 30 below zero, particularly when wind was present. The process began with skin temperature dropping below freezing. Ice crystals formed in tissues, damaging cell structures. Blood flow to extremities decreased as the body prioritized protecting core temperature. Reduced blood flow accelerated cooling of hands, feet, ears, and face. Ears, noses, and faces were most vulnerable when protective gear was inadequate. Standard issue cold weather gear included hats and hoods, but these did not always provide complete facial protection. Soldiers learned to improvise face coverings from scarves or extra clothing, but these could interfere with vision or breathing. The choice between protecting the face and maintaining vision and breathing was a constant balance. Guards and sentries who needed to observe carefully often accepted facial exposure and suffered frostbite as a result. Hands and feet suffered frostbite when gloves or boots were insufficient, or when soldiers had to remove gloves to perform detailed tasks. The thick mittens issued for extreme cold protected hands well, but made it impossible to operate weapons, perform maintenance, or handle small objects. Soldiers needed thinner gloves for dexterity, but these provided less protection. The compromise often involved wearing thin gloves inside mittens, removing mittens for tasks requiring dexterity, then replacing them quickly. Even brief exposure of hands in thin gloves could cause frostbite during extreme cold. Feet presented particular challenges because boots enclosed them completely, preventing easy monitoring. Soldiers could not see their feet to check for frostbite symptoms. The first indication was often numbness, but numbness also resulted from simple cold without tissue damage. By the time pain or other symptoms became apparent, significant damage might have occurred. Boots that fit well in moderate temperatures could become tight when worn with heavy socks, restricting circulation and increasing frostbite risk. Boots that fit properly with heavy socks might be loose with lighter socks, allowing cold air to enter. The initial symptoms included numbness and white or grayish skin. The affected area felt hard to touch, indicating frozen tissue. If exposure continued, tissue damage became permanent. As tissue froze, ice crystals destroyed cell structures. Blood vessels were damaged, reducing circulation even after rewarming. In severe cases, Gangrene developed as tissue died from lack of blood flow. The progression from initial freezing to irreversible damage could occur quickly, sometimes within an hour of exposure. Medical treatment for frostbite under field conditions was limited. The standard procedure involved gradual rewarming of affected tissue, ideally using water at approximately 100 to 105 degrees Fahrenheit. This required warm water, which was often unavailable in forward positions. Heating water required fuel and containers, both of which were in limited supply. Improvised rewarming using body heat was safer than rapid rewarming but took longer and might not be effective for severe cases. Improper rewarming could cause additional tissue damage. Warming frozen tissue too rapidly could damage blood vessels and increase the extent of tissue death. Incomplete rewarming followed by refreezing caused more severe damage than if the tissue had remained frozen until proper rewarming could be accomplished. This created difficult decisions when soldiers with frostbite could not be evacuated immediately. Should frozen extremities be rewarmed in the field with risk of refreezing, or left frozen until evacuation to proper medical facilities? Different medical personnel made different choices based on their judgment of the situation. Once frostbite occurred, the affected individual's combat effectiveness decreased substantially. Soldiers with frostbitten feet could not march or even walk normally. Movement became slow and painful. Frostbitten hands could not grip weapons or perform manual tasks. Even after initial treatment, affected individuals required evacuation to rear medical facilities for definitive care. This evacuation removed trained soldiers from units and placed additional burden on medical and transportation systems. The accumulation of frostbite casualties over time created a drain on unit strength comparable to combat losses in some periods. A company might lose 10 or 20 men to frostbite in a week without experiencing any enemy contact. Over a month, these losses could reduce a unit to half strength. Replacements arrived to fill the gaps, but new personnel were often even less prepared for cold weather operations and became casualties themselves at higher rates than experienced soldiers who had learned survival techniques. Battalion and regimental aid stations tracked frostbite casualties and reported them through medical channels. The numbers grew steadily through the winter months. A division might report hundreds of frostbite casualties in a week. Across the entire force in Korea, thousands of soldiers suffered frostbite during each winter season. These casualties did not receive the attention that combat casualties drew, but their cumulative impact on unit strength and capabilities was substantial. Trench foot represented another cold-related medical problem distinct from frostbite. This condition resulted from prolonged exposure of feet to cold and wet conditions without freezing. Boots and socks that became wet from snow or perspiration and remained wet for days created ideal conditions. The combination of moisture and cold damaged skin and underlying tissue. Symptoms included swelling, pain, numbness, and in severe cases, tissue death similar to frostbite. Prevention required keeping feet dry and changing socks regularly, but clean dry socks were not always available in adequate quantities. Soldiers were instructed to carry multiple pairs of socks and change them daily, but this assumed regular resupply that did not always occur. In extended operations away from supply points, soldiers wore the same socks for days or weeks. Even when dry socks were available, changing them required removing boots, which exposed feet to extreme cold and created frostbite risk. The process of changing socks in extreme cold required finding or creating shelter from wind, removing boots quickly to minimize exposure, drying feet if possible, and putting on dry socks before feet froze. This process in 20 below zero temperatures was challenging and dangerous. Some soldiers chose not to change socks rather than risk frostbite during the change process. This decision reduced trench foot risk in favor of maintaining immediate protection, but it represented a choice between different types of cold injury rather than prevention of injury. Shelter became a critical survival requirement during extreme cold. Tents provided some protection from wind and snow, but offered limited insulation. The canvas or nylon tent material blocked wind and precipitation, but did not prevent cold air from entering or warm air from escaping. Temperatures inside an unheated tent might be only a few degrees warmer than outside. During extreme cold with outside temperatures at 30 below zero, an unheated tent interior might measure 25 below zero. This reduction in wind exposure helped, but did not create genuinely warm shelter. Heating tents required stoves and fuel, both of which were in limited supply. Small portable gasoline stoves could warm a tent enough to prevent freezing, but not enough to create genuine comfort. A properly functioning tent stove might raise interior temperature to just above freezing, perhaps 35 or 40 degrees. This felt warm compared to outside temperatures, but remained cold enough that water could freeze and soldiers needed to remain in sleeping bags or heavy clothing. The warmth differential between inside and outside a heated tent created condensation that froze on tent walls and equipment. Breath and body heat generated moisture that condensed on the cold tent material and froze. Over days, tents accumulated thick layers of ice on interior surfaces. This ice added weight that could collapse tents and created wet conditions when any warming occurred. Equipment stored in tents became covered with frost that had to be brushed off before use. The ice accumulation reduced tent volume and created uncomfortable conditions even when stoves provided some heat. Fuel allocation for tent heating competed with other uses, including vehicle operation and cooking. Units received limited fuel supplies through logistics channels. Commanders had to decide how to distribute fuel between competing needs. Using fuel for tent heating meant less fuel for vehicles or cooking. These allocation decisions affected soldier comfort and morale, but also affected operational capability. Warm soldiers were more effective than cold soldiers, but immobile vehicles reduced tactical options more severely than uncomfortable soldiers. Soldiers learned to accept tents as windbreaks rather than warm shelters and adjusted expectations accordingly. Sleep in a heated tent was better than sleep in the open, but it remained cold and uncomfortable. Soldiers wore multiple clothing layers while in sleeping bags inside heated tents. Even under these conditions, extremities often became cold enough to wake soldiers during the night. The quality of rest in these conditions was poor, and soldiers accumulated sleep debt that affected performance. Foxholes and fighting positions offered even less protection than tents. These positions provided cover from enemy fire, but almost no protection from cold. Digging into frozen ground required extensive effort with picks and sometimes explosives to break through the surface. The ground in Korean winter could freeze to depths of several feet. Creating a fighting position deep enough to provide adequate cover might require hours of work with specialized tools. Soldiers often created shallow scrapes rather than proper foxholes simply because the frozen ground defeated their efforts. The holes provided tactical cover, but no protection from environmental conditions. A soldier occupying a foxhole during extreme cold faced direct exposure to wind and low temperatures. Snow could accumulate in positions, creating wet conditions that contributed to cold injury. Some positions flooded with water during the day when any warming occurred, then froze solid at night, creating ice-filled holes that were unusable without extensive clearing. Snow could be packed around positions to create wind breaks, but this required time and effort. Building snow walls or roofs required moving and packing large quantities of snow. The construction work generated heat through physical activity, but exposed soldiers to cold during the construction process. Once built, snow structures provided good insulation and wind protection, but they required maintenance as wind eroded them or new snowfall changed their shape. Some soldiers learned to create improvised shelters using ponchos, blankets, or parachute material stretched over fighting positions. These covers blocked wind and trapped some heat, creating marginally better conditions. The shelters had to allow observation and firing ports while providing protection, creating design challenges that soldiers solved through trial and error. These field-expedient shelters helped but could not eliminate exposure to extreme cold during extended periods in defensive positions. Food became both a practical necessity and a morale factor during extreme cold. The body required more calories to maintain temperature in cold conditions. Basal metabolic rate increased as the body burned more energy to generate heat. Physical activity in cold weather consumed additional calories beyond the increased baseline. Soldiers operating in extreme cold might require 5,000 or more calories daily to maintain body weight and performance, compared to perhaps 3,000 calories in moderate conditions. Standard rations provided adequate calories in theory, approximately 3,000 to 3,500 calories per day from C rations or other field rations. However, this fell short of actual requirements during extreme cold and heavy activity. Over days and weeks, soldiers lost weight and physical capacity. The gradual degradation in condition affected performance in ways that became apparent only over time. A unit that appeared functional in the short term might be approaching exhaustion after weeks of inadequate caloric intake. The food itself presented problems in extreme cold beyond simple caloric content. C rations, the individual combat rations issued to soldiers, froze solid at temperatures below about 20 degrees Fahrenheit. A frozen C ration was essentially inedible without thawing. The canned components became solid blocks of frozen food that could not be consumed. Eating frozen food lowered body temperature by requiring energy to warm the food to body temperature. This negated some of the nutritional value and contributed to cold stress. Heating rations required fuel and time, both limited resources. Soldiers carried small heat tablets designed to warm C rations, but these tablets provided minimal heat and worked poorly in extreme cold and wind. Heating a can of frozen C rations might require multiple tablets and considerable time. In some cases, soldiers gave up on heating and consumed rations partially frozen, accepting the discomfort and reduced nutritional value as preferable to waiting. Hot meals prepared at unit level required field kitchens and supply lines capable of delivering fresh food, which were often not available in forward positions. Battalion or company kitchens could prepare hot meals when logistics permitted, but these kitchens were typically located well behind front lines. Getting hot food to forward positions required insulated containers and transportation, often over difficult roads. The food that started hot at the kitchen might arrive merely warm or even cold after transport. Despite this, hot meals represented important morale events that soldiers anticipated and appreciated. Water presented similar challenges to food. Soldiers required water to maintain hydration, perhaps 3 to 4 liters daily under normal conditions and more when active. Dehydration contributed to cold injuries by reducing blood volume and circulation. Maintaining hydration in extreme cold proved difficult because water froze and because thirst sensation decreased in cold conditions. Soldiers often did not feel thirsty even when dehydrated. Canteens froze solid in extreme cold, often within hours of filling. A canteen carried on a soldier's belt or in a pack would freeze completely at 20 below zero. The ice expanded and sometimes cracked canteens or made them difficult to open. Keeping canteens inside clothing prevented freezing, but was uncomfortable and limited capacity. A 1-quart canteen kept inside a parka provided limited water but took up space and pressed against the body uncomfortably. Melting snow provided water but required fuel for heating and containers for melting. Units established procedures for melting snow when possible, designating personnel to maintain a supply of potable water. This required constant attention and significant fuel consumption. The water produced had to be distributed to soldiers, requiring containers and a distribution system. Some units never achieved adequate water supply despite efforts, operating continuously partially dehydrated. Consuming snow directly lowered body temperature and could contribute to hypothermia. The energy required to melt snow internally and warm it to body temperature was substantial. Soldiers who ate snow to quench thirst actually increased their heat loss and cold stress. Education about this danger helped, but thirsty soldiers sometimes consumed snow anyway when no alternative existed. Units established procedures for providing hot drinks when possible, recognizing that warm liquids served both practical and psychological purposes. Coffee, hot chocolate, and soup provided hydration, calories, and warmth. The psychological boost from a hot drink exceeded its physical benefits. Soldiers valued hot drinks intensely, treating them as rewards and morale enhancers during periods of extreme hardship. Getting hot coffee to forward positions became a priority for many unit commanders who understood its importance beyond simple nutrition. The cumulative effects of cold, inadequate food, insufficient water, and poor sleep created a downward spiral in soldier condition and performance. Each factor contributed to reduced effectiveness individually, and the combination accelerated degradation. Soldiers became weaker, less alert, more prone to errors, and more susceptible to injury and illness. Medical personnel observed that soldiers who endured prolonged extreme cold became more vulnerable to disease and slower to recover from injuries. Commanders at all levels struggled with decisions about how long to maintain operations before rotating units to rear areas for rest and recovery. Operational requirements pushed toward keeping units in position, while soldier welfare argued for regular rotation to prevent complete breakdown. Different commanders reached different conclusions based on their assessment of tactical necessity versus human limits. These decisions affected casualty rates and long-term unit effectiveness in ways that were difficult to measure precisely. The Korean winter of 1950 to 1951 proved particularly severe, with temperatures and conditions that exceeded even pessimistic planning assumptions. Soldiers who survived that winter carried memories of cold that remained vivid decades later. For many, the cold dominated their recollection of the war more than combat. The environmental challenge became the defining experience that shaped their understanding of Korea. The lessons learned during that first Korean winter influenced military policy and preparation for subsequent winters and for future operations in cold environments. Cold weather training programs expanded. Equipment procurement prioritized items proven effective in Korea. Medical protocols for cold injuries improved based on Korean War experience. Despite these improvements, subsequent winters in Korea remained challenging, demonstrating that while adaptation was possible, overcoming extreme environmental conditions was not. Understanding the impact of cold on the Korean War requires recognizing that environmental casualties were not anomalies or failures of planning, but inevitable consequences of operating in conditions that exceeded human tolerance without extraordinary support measures. The cold killed and injured soldiers throughout the war, creating losses that affected operations as significantly as enemy action. The strategic impact of these environmental casualties shaped campaign planning and contributed to operational patterns that defined the war's later stages. Winter in Korea was not merely a backdrop, but an active factor that influenced outcomes independent of tactical or strategic decisions. The cold that killed as much as the enemy demonstrated that in warfare, nature can impose costs equal to those of combat, costs that must be paid regardless of military capability or determination. If you enjoyed this Korean War story, subscribe.